Hello, physical science. So today we're going to talk about temperature, energy, and phase changes. So first of all, let's talk about changes in energy, energy transfers. So energy can be transferred into a system or it can be transferred out of a system. If it's transferred in, it's called endothermic. Now we've talked about some endothermic phase changes like melting, for example. Okay, melting would be an energy transfer in. And on the other side, another example here, exothermic. That is when energy goes out or exits. For example, freezing would be an exothermic phase change, that is. Okay, so the question really is, how is energy transferred? And energy is transferred by particle collisions. So one particle collides with another particle and it transfers its energy. So in the lab, we heated some water on a hot plate. So the energy went from the hot plate particles to the beaker particles by crashing into it. And from the beaker particles started moving faster and they crashed into the water particles. And that's how those particles transfer energy, by collisions. So the question is, what happens to a solid when heat energy is added? And you might think about ice if we're talking about a solid here. So the particles will always be affected. Now there's two options. Either they can spread apart and break connections, and this would be called a phase change. Or we could say a state change. Remember, phase and state mean the same thing. Or the particles could move faster. Now faster particles means that the temperature goes up. Remember, temperature measures how fast the particles go. So you could have an increase in temperature. Now the key here is to remember the words either and or, because it's an either or thing, not both of them. Alright, so if we have this happening where heat energy is added to a solid, what you get is you can follow it through with a warming curve. Now when you make a warming curve, there's going to be three distinct parts to it. Okay, and let's pretend this is for water. So we have right here, we'd have part A. You see it's kind of flat here in part A, not much change in temperature. Okay, and if we're talking about water, this would happen at about 0 degrees. And then you have this part right here, which we'll label as part B. Okay, and you can see in part B, you're having a rapid change in temperature. So what's going on there is, again, you're changing state. So if we look more closely at these points here, part A is when you are actually undergoing a phase change, and this is called melting. Okay, because remember, this we're talking about for water. Okay, specifically for water. So when it's at 0 degrees, that's when it's melting. So during part A, you're melting. So at the beginning of part A, you have a solid, and at the end of part A, you have a liquid. So if we zoomed in on only this part of the graph where we have part A, we could think about the particle diagram here. So we could look at the particles at the very beginning, and we would say that they're very close together because they are a solid. And you can see the particles are all close together in that particle diagram. Now if we look at the other half of the A part of the graph, when we're over here, now the particles have become a liquid. And in a liquid, the particle arrangement is no longer as rigid and the particles are further separated. So this energy that we added during this part of the graph right here, during that time of the graph where we added energy, that energy was being used to break the connection between the particles. So they go from being close together to this state over here where they're farther apart. So we go from a solid to a liquid. So if we look at the next chunk of our graph here, and we're looking at the B chunk of the graph where it's a rapid temperature change, we have a liquid beforehand and we have a liquid afterward. So we have a liquid at the beginning of B and we have a liquid at the end of B. And the particle spacing is pretty much the same. The only difference is that our temperature is changing. And when your temperature changes, the speed of your particles changes. So up here at the top of the graph, the particles are moving much faster than they were down here at the bottom of the graph. And if we're talking about water, this difference is quite significant because up here at the top of the graph, this actually would be about 100 degrees because those particles have to get up to 100 degrees before they would start to evaporate or boil. And if we focus in on part C of the graph next, this is where boiling happens, and this is where the temperature is constant throughout. Okay, and boiling again is another change in state. It's when it goes from a liquid to a gas. And when boiling happens, again, your temperature is constant. But what's happening is those connections between those particles is breaking further. So the particles go from what they were right here at the beginning. Let me circle them. What they go at the beginning of C to at the end of C, where they are very far apart. So let's look at that a little closer. So we go here from this liquid to, at the end of part C in the graph, we would go to a gas. And in the gas phase, the particles are even further spread apart. And so we'd have particles that would be more like this. So the gas particles are going to be so far apart because that energy that goes into the particles during part C is actually helping them to break away further from each other. So one last little review here of our warming curve. So we have, again, this is for water, so our temperature here would be 0, and our temperature up at the top here would be about 100. Right here is where we have melting. And right here, in this part of the graph, is where we have boiling. And important to note, when you have melting or boiling, those are both state changes, and your temperature is constant. Okay, and in the middle part of the graph here, where the temperature is changing rapidly in the middle of this graph, that's where it's just making the particles move faster. Now, all that being said, what would happen to a substance when heat energy leaves the system? Okay, so we just looked at if you add energy. So now what if energy is leaving the system? So this would be for an exothermic. Okay, again, the particles will be affected, and either they're going to come together and form connections, or they will move slower. All right, two options. All this is going to do is flip our graph, and it's the same exact concepts, except now, since energy is leaving the system, right, because it's exothermic, now we're going to have a cooling curve. In our cooling curve, it's going to have a flat part at the top, and this is where we will have condensation. So during condensation is when it goes from a gas to a liquid. And then we'll have this part right here where it's cooling. And when it's cooling, the particles will be slowing down. And then we have this very last part of the graph, another little flat part of the graph. And this is where freezing would occur. So particles are making those connections and forming into a solid. So freezing. Okay, and one thing I want to point out too, the freezing temperature of water is 0. The condensation point of water is 100. Okay, so the boiling point and the point it condenses at are the same temperature. The freezing point and the point to melt at, same temperature. Okay, so a couple of key points here. You want to remember that energy can be transferred in or out of the system. If it comes in, it's endothermic. If energy leaves the system, it's exothermic. Okay? You want to remember that changes in energy always affect the particles. And you can have either the state changing or the temperature changing. Okay? And if the temperature changes, that's when you're talking about motion of the particles. But the key to remember here is that they don't both happen at the same time. Not both at the same time. So just remember, the temperature is not changing as something melts. Not changing. Okay? A warming or cooling curve will show how energy changes affect temperature. The flat parts on the graph indicate state changes, where the particle connections are changing. Steep rises on the graph indicate temperature changes, and that's where particle motion is changing. And I just want to reiterate two vocabulary terms here. Temperature, a measure of particle motion. Okay, temperature is a measure of particle motion. And if you have a high temperature, it just means you have fast particles. Low temperature is slow particles. And a heat is the measure of the energy transfer. Okay, so again, temperature measures particle motion, heat measures energy. So that's all for now. Thanks.